and you'd like to broaden your knowledge of programming fundamentals, then roll up your sleeves because this course is for you. We'll walk through understanding and using. If you've gotten a taste of programming and you'd like to broaden your knowledge of programming fundamentals, then roll up your sleeves because this course is for you. We'll walk through understanding and using programming patterns and syntax like loops and collections that are common to many languages. We'll also cover the basics of processes like debugging and program planning that programmers routinely need to do while writing applications. Now, if this feels like it might be a huge leap for you, don't worry. We're not going to be writing super complex programs here. But we will go through some concepts that are beyond the basic building blocks you may have worked with so far. Throughout the course, I'll be illustrating these more advanced concepts and trying to help you wrap your head around what these terms mean so that you can continue building your skills as a programmer. I'm Sasha Vodnik, and I've been programming computers since I was a little kid. If you're ready to take your next step in the fundamental concepts that underpin computer programming, then this LinkedIn Learning course is for you. In this course, I assume you're already familiar with a few basic programming concepts, specifically variables, functions, and conditional logic. If any of these don't ring a bell, or if you could use a little brushing up, check out the Programming Foundations Fundamentals course in the library. I'll be walking you through example code in this course using the Python programming language. Python syntax is pretty straightforward, so if you have some experience programming but not with Python, you'll probably be able to follow the examples just fine. But if you want to understand the syntax for basic Python commands, Programming Foundations Fundamentals is a great starting point for that too. I'll be using a Mac in this course, but you can also work through it using Windows or Linux. I'll also be coding in Python. To use Python on a Windows machine or on a Mac, you have to install it. If you don't already have it installed, start by opening a web browser and going to python.org/download. I'm using Python version 3 in this course, so you can download the latest version that starts with 3. I'll be using Python 3.8.0, which was the current version while I recorded this course, but you may see a different version number. As long as it starts with 3, you should be fine. Once you've downloaded Python, just open the installer you downloaded and follow the prompts to install it. You can use any code editor to work through this course. I'll be using Visual Studio Code, so if you want your screen to match mine, you'll want to install and use that as well. Visual Studio Code is free to download and use, and it's available for Mac, Windows, and Linux. One of the first things I do when I install Visual Studio Code is to turn on word wrap. That ensures that a line of code that's longer than the editor window will wrap to the next line, so I can see it all rather than it getting cut off at the edge of the window. To turn on word wrap, you can click the View menu and then click Toggle Word Wrap. You'll also want to add an extension to Visual Studio Code to make it easier to work with Python code in the editor. On the activity bar on the left side of the window, click the Extensions button. Then, in the search box, type Python. In the results, look for the Python extension that's written by Microsoft, which is right here. Clicking that gives you a little more information on the extension, and when you're ready, click the green Install button to install it. When you're done, the editor may prompt you to restart it to enable the extension, and you'll be prompted to install a couple other tools as well, which you should go ahead and do. After the extension is installed in Visual Studio Code, it should prompt you to install PyLint, which is another really useful tool. You should click Install to make sure this tool gets installed. Now, the first time I installed the Python extension, I closed out of the PyLint dialog box too early. Gah! If you did that too, if you already dismissed that dialog and you still need to enable PyLint, check out the Visual Studio Code documentation for instructions on how to enable that. You may also be prompted to install Python command line tools by your operating system. If your system suggests this, follow those prompts to install those tools. If any of this sounds confusing or unfamiliar, check out Programming Foundations Fundamentals, which walks you step by step through this process. Now that you have everything installed and configured, you're good to go. Let's dig in. Despite my best efforts at digital organization, sometimes I have projects that involve working with sheets of paper. Lots of sheets of paper. If I have enough room, I can just spread them all out and then grab the one I need for each task that I'm doing. But when the paper multiplies, I don't have enough room for it all. So I make a pile. And that makes sense when my papers are related, especially if they're papers that I'll need to use together. A pile keeps related papers together and keeps them organized. It also makes sure that when I know the type of information I need, but not the specific sheet it's on, I can easily grab all of them. If my papers start multiplying, it can make sense to organize them into groups. I can grab some file folders, add some labels. I can even hang them up for easy access. Even though I have more papers, the labels make it easy for me to find specific papers when I need them. Grouping similar items together is also useful in programming, and it's so common it has a name, a collection. Like a pile of papers, a collection in programming lets me group similar items together using a single name, which is known as a variable. Organizing data in this way has a few advantages. First, creating a collection uses your code structure to indicate that multiple pieces of data are related. So rather than storing a bunch of values and needing to identify which ones are relevant for different processes in my program, all the related data is grouped in a single place. Second, using a collection avoids creating a potentially huge number of variables to track within my code. Instead, all the related data is stored under the same variable name, with syntax to retrieve or change the specific data I need at any point. And finally, it's common to need to access multiple related pieces of data and then perform the same process on each piece of data. A collection offers simplified syntax for performing this type of process. Collections can take different forms, and programming languages vary in the types of collections they support. Learning how to create and use collections in programming will help you to write more efficient and better organized code that can easily work with data from a wide variety of sources. I have a bunch of sheets of paper here that contain related information. I could keep them all laid out on my desk so I can easily pick up any one of them at any time. But I don't have the desk space to do that for very many sheets. And if I need to do something like copy or scan the whole set, doing it a sheet at a time is pretty inefficient. Instead, I can gather them all up into a stack. Knowing that these documents are all related means I know that if I need, say, one of the contracts for a certain project, I just need to look in the stack. And if I want to copy all of them, for instance, I can just stick the whole stack in the auto feeder on my copier and let the machine do the rest. One of the simplest types of collection in programming groups pieces of data together in a certain order and assigns the collection a name. In Python, this type of collection is known as a list. To create a list, I simply specify a variable name, enclose the value in square brackets, and then for the collection, provide values separated by commas. In the list.py file, I have 4 variables named city1 through city4, containing the names of 4 cities where a fictitious company has offices. This is all related information, and grouping it together makes sense, so I'm going to turn it into a list. I'm not going to need the 4 existing variables in my code anymore because I'm going to replace them with a list. But I still want to keep them in my file so I can refer to them as I build out my list. I can do this by making them into comments, which is any text that's not actually part of the program. In Python, comments start with a hash symbol. Anything on a line that follows a hash symbol is ignored when the program is executed. However, it's still available for developers to read, which is super useful in this case because I still need the data in those variables to create my list. So I'll add a hash at the start of each of these lines, and my editor immediately formats that line as a comment after I type. And I'll add that space in there just to make things look a little bit better. And then below that, I'll make a new variable called cities. And for its value, I'll type an opening square bracket, and my editor automatically inserts the closing punctuation there, which is great. When I press enter, I get a new line, automatically indented and ready to go for some content. Now, I could type the whole value for my list on a single line, but it's much easier to read when each item is on its own line. And in a list, the line breaks and tabs don't change the meaning. So on this new line, I type that first value, including the quotes, so quote Tokyo, followed by a comma, and I press enter. And then I just do the same thing for the remaining items. So taking the value from each of those variables, moving it down here as a string, and adding that comma at the end, and adding a comma at the very end for good measure. Now all 4 of my variables are in a list, and they're all sharing a single name. So by grouping my variables together in a list, I've organized my code, and I've made it clear that these values are related. Sometimes simply grouping data doesn't meet my organizing needs. For instance, say I've organized all my papers for a project into stacks, receipts, correspondence, and forms. Without a label, it can be hard to remember what's in which pile, and I certainly just can't stack it all up together without losing my organization. With papers, I can use a system like hanging file folders, and I can indicate the category on the file folder tab. When I'm done with the box, I have all the documents grouped and labeled for easy access, but stored within a single project. Like my papers, related data in my program sometimes needs a more complex approach to organization as well. Many programming languages support a rich collection type that lets you store related information, but with a label for each item. In Python, the dictionary data type serves this function. To create a dictionary, I specify a variable name, enclose the value in curly braces, and then for each item in the collection, I provide a tag name followed by a colon and a value, with commas separating the different values. In the dictionary.py file, I have 4 variables, which store 4 of the state symbols of California: the bird, the animal, the flower, and the fruit. These are all state symbols, and so it would make sense to group them together. But I want to retain information on what type of symbol each value is, and I can do this with a dictionary. So I'll comment out the existing variables, and I can use a shortcut for this. So I'll start by selecting the text, and then most editors support Command/ as a keyboard shortcut to comment out selected code. Then below, I'll make a new variable called California symbols, and for its value, I'll type an opening curly brace, my editor provides the closing curly brace, and when I press enter, I automatically start in a new line with an indent ready for me to add some content. For my first value, instead of state bird, I'll just use the name bird, because the variable name already makes it clear that this is a state symbol. Then I'll type a colon, and I'll type the value, which is California quail, as a string. After that closing quote, I type a comma and then press enter. So the first value has a label of bird and a value of California quail. And that comma at the end separates it from the value that follows. So I'll repeat this for the remaining 3 values. So using the string animal for the second one, a colon, then I'm just going to copy and paste. So I'll grab grizzly bear, paste that in, type a comma, and on a new line, flower. I will copy California poppy and paste that in, add a comma, and then finally fruit, colon, and I'll just type avocado and put a comma at the end for good measure. Like a list, I have all my values grouped together in a single variable. But unlike a list, In this dictionary, I can still label each item, providing more information and giving me more flexibility in how I work with the data. Both lists and dictionaries allow me to store related data using a single variable name. To access and use individual pieces of data in either of these collection types is slightly different than simply referencing a variable name, but it's pretty straightforward to do with the proper syntax. Each item in a list is automatically assigned a consecutive number based on its position, known as an index number. It's important to note that index numbering does not start at 1. It starts at 0. This system is common in a lot of programming languages, and working with list indexes is a great way to get your feet wet with it. Within a list, the first item has an index of 0, the second item has an index of 1, and so on. To reference the data at a given list index, you reference the variable name followed by the index number in square brackets. In my list.py file, my cities list contains 4 pieces of data, strings that represent city names. The first string, Tokyo, will have an index value of 0, and the last string, Buenos Aires, will have an index of 3. I want to print the second city name, Dakar, to the terminal. So below my variable, I'll type the print command and open parentheses, and my editor shows me documentation, which I can dismiss by hitting escape. Then in the parentheses, I reference the variable name that stores the list, cities, and then in square brackets, the index number for the second piece of data. Now, because index numbers start at 0, Tokyo would be 0 and Dakar would be 1. So I put 1 in the square brackets, then I save my code, and then I'll run it. And there, in my terminal, Dakar is printed. Referencing data in a dictionary is similar to a list reference. To reference a dictionary item, I start by referencing the name of the variable that stores the dictionary value. A dictionary doesn't use index numbers, though, because each item in a dictionary has a label. I'm going to switch to the dictionary.py file. To reference a dictionary value, I simply add square brackets after the variable name and specify the label in quotes. I want to print the name of the California state flower to the terminal. That's stored in my California symbols dictionary with the label flower. So I can add a print statement, open those parens, and press escape to get rid of that extra documentation. Then I'll type the name of the variable, California symbols, and once I start typing, my editor automatically prompts me what it thinks I'm typing. In this case, it's right, and I can simply press tab to autocomplete that. Then I'll open my square brackets, and in those square brackets, instead of a number, I just need the label name, which is the string flower in quotes. Then I can save that, I can run my code, and now California Poppy is printed to the terminal. Collections provide a way of creating organized code while still allowing you to work with individual values within them pretty easily. Collections also lend themselves to programming techniques such as iteration, which lets you easily work with all the values in a collection at once. Being able to work with data in collections adds a really useful tool to your programming toolbox. Collections, like Python's lists and Python's dictionaries, let you organize related data. And we're primarily going to be using Python in this course. But it's important to understand that across programming languages, collections can actually vary a lot. In Python, each item in a list can be of any data type, so you could combine strings, numbers, and other types of data like Boolean values all in the same list. But other languages like C++ require that all values in this type of collection must be of the same data type, for instance, containing all strings or all numbers, but no combination of these or other types of data. Another factor in collections is whether the data stored in them can be changed. In Python lists or Python dictionaries, you can add or remove items, or you can change the value of an existing item. We refer to these collections as mutable, meaning they can be changed. But some programming languages support collections that are immutable, meaning that their values cannot change after they're created. In fact, Python itself lets you create a collection known as a tuple, which is essentially an immutable list. Once you create a tuple, you can't change it. And this can be especially useful in coding. When you're working on a large project, for instance, with other developers, using an immutable collection like a tuple can help ensure that data that shouldn't be altered, like a collection of locations, remains unchanged. Even when programming languages share collection types, a wide variety of names are used for common collections. For instance, what's known as a list in Python is called an array in JavaScript and C++. Python dictionaries are known variously as associative arrays, maps, or tables. So, as you build more complex programs, your organizational requirements may influence which language you choose based on the characteristics it offers for its collections. It's time for a challenge. Ready to try your hand at working with collections? The start file for this video includes two groups of variables. The first group stores the names of the 4 stars that are closest to the Earth. The second group names the highest peak on each of Earth's 7 major tectonic plates. For the first group, your task is to replace the variables with a list named stars, preserving the order shown. Then create a statement that prints the name of the 4th nearest star. For the second group of variables, you need to create a dictionary named peaks that stores all of the values using the variable names as labels. Then create a statement that prints the name of the highest peak on the Pacific Plate. Your output should look like this. This challenge should take you about 15 minutes. When you're done, join me in the next video and I'll walk you through how I approached it. Have fun! Hope you had fun with that challenge. You might have had questions while doing it, or you might have had a moment when you weren't sure about what to do next. If you did, that's totally normal. Understanding and working with programming concepts takes practice. Trying your hand at this challenge is a first step in building those muscles. Let me show you how I tackled this one. My start file has 2 sets of variables. Let's start with the first set, the 4 stars nearest to Earth. This is essentially an ordered list, and a Python list is an ideal choice for grouping this data because the order matters. So I'll start by commenting out those existing variables, and then I'll create a new variable called stars. After the equal sign, type an opening square bracket, and then I press enter, and I'm ready to enter values. These will just be strings separated by commas. I could copy and paste, but I'm a pretty fast typer, so I'm going to type these out. So we got Sol and a comma, Alpha Centauri and a comma, Barnard and a comma, and finally Wolf 359 and a comma. See that comma I put at the very end? It's not technically necessary, but it's a common practice to include this at the end of a list or array in a number of languages. With that final comma there, if I want to go back later and add another value, I don't risk forgetting to add the comma as a separator, which would introduce a syntax error. Next, I want to print the 4th nearest star. I'll use a print statement, and in the parens, get rid of that pop-up. For the value I want to print, I specify the stars variable, square brackets, and then in the brackets, I need to use the index number for the 4th value. Remember how the array elements are numbered? They start at 0. That means I have 0, then 1, then 2, and then finally an index of 3. So I type 3 in the square brackets to reference the 4th item. I'll save and I'll run in the terminal. And there's Wolf 359, the 4th closest star. So I finished the first part of the challenge. Now onto the other set of variables, the highest peaks on various tectonic plates. Notice that each of the variable names describes the data it stores. So when we're looking at grouping this data together, a dictionary makes sense because it allows us to preserve both those labels and their values. I'll start by commenting out those existing values, and then I'll create a new variable called peaks to store my dictionary. After the equal sign, I'll type that opening curly brace and press enter. I still enter my content line by line, but remember there are a couple differences from the original variables above. First, the labels need to be formatted as strings, so surrounded by quotes. And then instead of an equal sign between the label and the value, I have to use a colon instead. And finally, I have to remember that comma at the end of each line. I'm going to type the plate names and then copy and paste the peak names. So African, colon space, and then I'll just copy and paste Kilimanjaro. Then a comma and press enter. And the same for each of the rest. It's pretty common when you're working with a dictionary like this that you're actually bringing the data in from somewhere else. But in this case, we're just typing it up. And a couple more. Pacific. And then finally, South American. And that final comma. And finally, to print the name of the Pacific Peak, I use a print statement. And in the parens, I'm going to reference the name of the variable, which is peaks. And then in square brackets, instead of needing to identify an index number, I simply type the label text for the value I want to print in quotes. So in this case, that's Pacific. And remember that capitalization is important, so I need to make sure here that I use the capital P, just like the tag in the dictionary that I created. Then I can save that, run that code in the terminal, and now in addition to Wolf 359, I've printed Mauna Kea, which is the peak on the Pacific Plate. I hope you enjoyed the challenge. If you got it to work on your own, congratulations. And if not, that's okay. In fact, part of programming is testing your limits, identifying what you need to brush up on, and then practicing. Keep at it, and you'll be building your own programs containing collections in no time. Folding laundry can be a pretty repetitive task. For instance, when my t-shirts come out of the dryer, I need to take one from the pile, fold it, then take another one from the stack, fold it, and keep repeating until the stack is empty. I'm only doing one task, folding a t-shirt, but I have to do it multiple times to different items until I'm done. This process is so common in programming that there's a specific term for it, iteration. When you write code that iterates, it repeats the same procedure multiple times until it reaches a specified endpoint. Code that iterates is often described as a loop because the process moves from beginning to end and then starts over again at the beginning, possibly hundreds or even thousands of times. Every programming language has syntax just for iteration. To write code that iterates, you commonly need a few specific pieces of information. First, you need to specify the data that's being iterated through. This might be a collection that needs the same thing done to each item, like a set of prices in a shopping cart. Second, you need to describe what should happen to the data on each iteration. For instance, you may want to calculate a discount percentage for each price in a shopping cart, so a user can see the savings on each item. Finally, you need to indicate when the loop should stop. With a collection, this is often simply when there are no more items. But you could also have a more complex condition, such as when the total discount has reached a maximum amount, after which no more discounts should be calculated. You may have heard the term infinite loop, which describes a bug that can occur when the ending condition is omitted or specified incorrectly. This creates a situation where the loop never stops, which may result in a program that freezes or stops responding, as well as heavy demand on the computer running the program, which could slow it down or cause it to heat up. When written correctly, though, loops are incredibly useful tools in all sorts of programs. With a little practice, you'll be able to use loop structures to build code that's both flexible and compact. To make an omelet, as the saying goes, you have to start by breaking a few eggs. If I want to make a 3-egg omelet, I need to crack 3 eggs, one at a time, into my mixing bowl. So I grab the first egg, I crack it, and I drop the white and the yolk in the bowl, and I put the shell aside for my compost pile. Then I repeat with the second egg, and finally with the third. And now that I'm through with all the eggs, I can move on to the next steps in my process: seasoning, beating, and cooking everything up. We use iteration in programming all the time. In Python, you can create a loop using the for keyword. In the start file for this video, I have a list called spices that stores the names of 4 spices I like to use when making omelets. To print the contents of my list, I can use a for loop. Let's try it out. I'm going to type for spice in spices, colon. The for statement lets us specify a variable name that we can use in each iteration of the loop to reference the current value. The variable name can be anything, and here I'm using the variable name spice for clarity, because each value I'm working with is a spice, although we can debate about whether or not salt is a spice, but I'm the cook here, so it's a spice. The next word, in, is a Python keyword. It indicates that what follows is the set of values that we want to iterate through, and for that set of values, I'm referencing the spices list. Now remember that in addition to the data I want to loop through, I need 2 other pieces of information for a loop. One of those is where to stop. When I specify a list as the data to iterate through, my for loop will automatically end with the last value in the list. To specify what I want to do with each value, I create a new indented statement under the for statement. And I'm going to use the print function and in parens, the word spice. My for statement starts with the list of spices. It assigns the first value to the spice variable and then executes the print statement. Then it moves to the next item in the list and repeats until there are no more items in the list. In this for statement, the spices list itself defines when the loop should start and when it should end, and the print statement specifies what the program should do with each value. I'll save my work and then execute the code in the terminal. The values of the spices list are printed one after the other. Remember that any statements after a loop are executed only after the loop is finished, but it's important not to indent them or they'll be executed in each iteration. For instance, I want to print no more boring omelets after all my list items are logged. What happens if I put that after the print spice statement and indent it at the same level? So print and then a string, no more boring omelets. Well, let's save and run. The no more boring omelets phrase is printed after the name of each spice. This is because the indentation makes that final statement part of the for loop. That's not what we want. To fix that, I can simply remove the indent. This takes the statement out of the loop. And now it should be executed only after the entire for loop is finished. So I'll save, and I'll run that again. And this time, the names of all my spices are printed first, and then my final statement is printed just once at the end. Using loops with lists or other collections allows us to work with sets of data without writing repetitive code. By combining iteration with other programming tools, you can build your own complex and amazing projects. Screwing something in is fundamentally an iterative process. To tighten down this C-clamp, I need to get it in place, do a turn to the right, and check if it's tight. It's not. It's still loose. So I need to reposition my hand, give it another turn, and check again. And I need to just keep doing that until it's tight. Only at that point do I stop my loop. This type of iteration doesn't rely on a collection of things to iterate through, like, say, folding laundry. Instead, it's simply something that needs to happen repeatedly until it's done. In the same way, sometimes when I'm writing code, I need to continue a loop until the program arrives at a certain state. In Python, you use a while statement to create this type of loop. To get started with a while loop, we commonly use a variable that will be modified on each iteration through the loop. The name doesn't matter, but you'll often see the variable name I, which is short for iterator. I want to create a loop that counts to 100 by 5s. So I'll start with the value 5. Next, I need to specify my end condition. I do this with the while keyword, followed by a condition that evaluates to true or false. After each loop, this statement is checked. If it's false, the loop continues. But if it's true, no more loops happen. In this case, I want to count to 100, with 100 as the last number printed. So I'll use while I is less than or equal to 100, and I'll end that with a colon. After the while statement, I'm going to start a new line and indent, and I add any statements that I want to be executed on each loop. I want to do two things here. I want to print the current value of I. I also want to increase the value of I by 5 because I'm counting by 5s. So I'm going to use print I, and I'm going to use I plus equals 5. I'm going to save my changes, and then I'll run my code in the terminal. And scrolling up to the top of that output, I have a list of numbers starting at 5 and counting by 5 to 100. Any statements before and after the while construction are not part of the loop. So I can add a line at the top, for instance, a print statement. So I'm going to say print counting to 100 by 5s. And then at the bottom, below the last statement and not indented, I'm going to add a concluding statement. Print list complete. I'm going to save that. I'm going to clear my terminal and then run again. And scrolling to the top, I can see that my intro statement is printed first, followed by my series of counting to 100 by 5s, and finally my terminal statement, my last statement, list complete. While statements let us write code that moves our program along to a certain point before handing off control to other statements. It's time for a challenge. Ready to try your hand at iterating? In the start file for this video, I've created a list named fruits. It contains the names of 6 different fruits. Your task is to print the names of all the fruits in the terminal, each on a separate line. In addition, before the list, print a line that says our fruit selection. Your output should look like this. This challenge should take you about 5 minutes, and you'll want to use a for loop. When you're done, join me in the next video and I'll walk you through how I approached it. Have fun! Your challenge was to print each of the strings in a list and to print another line of text once before the strings. To print the items in the list, I need to iterate through the list and execute a print statement for each item. Because I have a list as a starting point, I want to use a for statement. After the keyword for comes the variable name that refers to the current item each time through the loop. Because this is a list of fruits, I'll use fruit as my variable name for clarity, but it's fine if you chose another variable name for your solution. And then the keyword in, and the variable that contains the list, which is fruits, followed by a colon. Then on a new line, I'm automatically indented. Remember that any statements I indent below the for statement are executed on each iteration. Here, I simply want to print the name of the current item in the list. So that's going to be print, and in parentheses, fruit. I'll save my code so far, and then test that out. And in the terminal, there's my list of fruits: apples, bananas, dragon fruit, mangoes, nectarines, and pears. The final step in the challenge is to add the text our fruit selection before the list. Now you might be tempted to put that after the for statement and before the print fruit statement. But remember that everything indented below the for statement is executed on each iteration, so we get the heading before each fruit name rather than just once at the start of the list. To add a title to the list, I need to add a print statement before the for statement. So I'll add the code at the top before my for statement, print, and as a string, our fruit selection. I'll put a colon at the end because it's a heading. Now my print statement for the title should be executed once, and then the loop will happen, which will print each fruit name. So I'll save that, I'll execute it, and there it is. I have the title, followed by each fruit name. Loops are super useful in programming, and they let you do all sorts of work with groups of data. If you want to challenge yourself further, try creating a new list containing numbers, and then use a loop to do a calculation on each of the values. Now that you know how to use loops, you've opened the door to building structures and working with data in your programs in all sorts of new ways. When you're first learning to program, Solving basic problems can be really useful in honing your skills. But as developers move on to more complex programs, it can become tedious to have to rewrite code to solve the same problem over and over. Fortunately, it's pretty easy to avoid these repetitive tasks. Across programming languages, developers often create code to accomplish basic tasks and then share it with the developer community for free. Instead of reinventing the wheel, you can simply find existing shared code that does what you need and then incorporate it into your program. This lets you focus on building out the custom parts of your programs. There are several different types of shared code, and the terms for these can vary from language to language. We'll take a look at types of shared code in Python as a starting point. The most basic type of shared code in Python is called a module. A Python module is a Python file that contains code, like variables or functions. I can make a module available in my own program through a process called importing, which involves referencing the file name in my own code. Then I can use the functions and other parts of the module anywhere I need them. Using a library is similar to buying a cake mix. The basic ingredients are measured and combined for you, saving you some time. But you still get to pick the shape of the pan, the type of frosting, and any filling or decoration you want to use. Sometimes it makes sense to use multiple modules together, so they're distributed and used in a group. In Python, this is called a package or a library. It's like buying a cake mix that also comes with a tube of frosting and some candles. Everything you need to get a birthday cake ready. Code can also be distributed in even larger groupings. When a set of code is not just used together, but used in a specific way, it's distributed as a framework. When you use a framework, you let the external code set the basic structure and flow of your program, and you customize it for your use case. It's like buying a birthday cake from a bakery. You may be able to select among a few flavors, and you can specify the basic decoration style, but the bakery will probably have a standard size and shape for all cakes. And then you can do any final customization you might like. Now, I enjoy baking, so I like to make a cake from scratch from time to time. And likewise, it can feel really good to write an entire app from the ground up instead of using external code. But when you're not excited about writing basic code, or you have a tight deadline and need to save some time, modules, packages, libraries, and frameworks can help you move on to the custom code you're excited about writing. When the application you're working on becomes large and complex, it's common to split your code into different modules as a way of organizing it. You can use modules shared by other developers, but you can also create your own. Let's try it out. In the start files for this video, I have a file called testmodule.py. This file contains a function called mult that accepts two numbers and then prints the result of multiplying them. This is something I might find useful in a lot of different programs I write, so splitting it out into a module makes it easier for me to integrate it into different applications I create. You might notice here that I'm using a Python syntax to print a combination of strings and variable values starting with the letter F. You can learn more about that by looking at Python documentation online. The app.py file is blank. This file is where I'm going to write the main code for my application. Before I can use the mult function for my module, I first have to import the module. Importing lets the Python compiler know that I want to reference code in a separate file. To import the contents of testmodule.py, I type import testmodule. This tells the compiler that I want to access code from a file called testmodule.py, which is located in the same directory as the current file, app.py. Next, I want to multiply 10 times 5 and print the result using the mult function in the module file. To reference a function from a module, I have to first reference the module name, followed by a period, and then the function name. So to use the mult function, I type testmodule.mult, and then in parentheses 10, 5. This statement tells the compiler to look in test module for a function called mult, pass it the values 10 and 5, and then work with the result of the function. Let's see what happens. So I'll save my work, and then I'll execute my code. And here in the terminal, I see the result of my call to the mult function in the test module, which prints the statement 10 times 5 equals 50. You may notice that Python adds the PyCache folder the first time you execute code that uses a module, and that's totally normal. I can continue coding in my app.py file using test module or any other module that I want. I could also easily use test module in any other app I work on just by copying the file over and importing it. In addition to creating your own modules, a lot of existing modules are freely available online for many programming languages. For Python, the Python Package Index is a widely used repository of modules that includes basic information on each module, as well as details on how to use it. If we scroll down on the Python Package Index website, I can see some of the trending projects and the new releases. No matter what language you're writing in, modules add a whole new level of organization and portability to your code. All the different types of external code available for programmers can be overwhelming, but getting the difference between libraries and frameworks can be especially challenging. Both are larger collections of software tools that help developers accomplish specific tasks. But while a library gives you a set of tools that you can use as you wish, like this cake mix and frosting, a framework essentially defines how you should accomplish a task, like this completed cake, where the shape, size, and frosting color are already set, leaving just the personalization to me. When you decide to use a framework, some decisions are already made for you. As long as you understand how to code within the framework, it can save you time. But if you're not ready to commit to a specific approach for the app you're building, or if there's no framework that meets the needs of what you're creating, then you can decide on your own approach to coding it up and use one or more libraries as tools to help you get it done. In Python, popular libraries include TensorFlow and Pandas for machine learning tasks, and NumPy and SciPy for mathematical manipulations. Widely used Python frameworks include Django and Flask, which are both used for web content management. Other modern programming languages have a wide variety of both libraries and frameworks available as well. In JavaScript, for instance, the Lodash library offers some general programming utilities, while the jQuery library provides tools for selecting and working with web page elements. Widely used JavaScript frameworks for building web apps include React, Angular, and Vue. When you're starting out with programming, the programs you write often don't need libraries or frameworks. I started out coding in JavaScript, and for a while, I got along just fine not using any of those. I built out basic web pages for friends and simple apps like a date picker and a countdown clock with nothing but basic JavaScript, and they worked great. So when you're just starting out, you won't necessarily need to dig into libraries or frameworks right away. But down the road, you might. So file this away. As you take on larger scale programming challenges, check out the libraries and frameworks available in whatever language you've chosen and see what they can do for you. They might be helpful. Construction block sets are made with a common connection system, so most any block can fasten to most any other one. This lets you take a set of blocks and put them together in many different configurations. A string in programming is a lot like a structure built out of construction blocks. Just as the structure is built out of individual blocks, you can think of a string as a collection of characters assembled together in a specific way. Those characters could be taken apart and reassembled differently, just like the blocks. One of the simplest and most common string operations in programming is concatenation, in which multiple strings are combined into a single string. In Python, as in many other languages, we use the plus sign to concatenate strings. In the beginning exercise file for this video, I've written code to prompt the user to enter a number, and then to print the value entered by the user to the terminal. I'll go ahead and execute this code, and at the terminal, I'll enter the number 50, and I see the number 50 printed at the terminal. Even though my program is prompting the user for a number here, whenever a user enters a value in response to the Python input statement, the result is treated as a string. This means that I can concatenate text to whatever a user enters by using a plus sign. So here, after the value variable name and before the closing parentheses, I'll type a plus for concatenation, followed by quotes, a space, and then is my favorite number. I'll save that, run it in the terminal, and when I type 50, now the program prints 50 is my favorite number to the terminal. This is a result of concatenating the string 50 with the string is my favorite number. But what if I wanted to do math with the number instead? Well, let's try and see what happens. I'll first add a print statement to label what I'm doing. Print when you multiply it by 10, this is what you get. And then another statement to print the value times 10. And that's going to be print value times 10. Then I'll save and I'll execute. I'll type 50 and my program prints 50, 50, 50, 50, 50, 50, 50, 50, 50, 50. My program has taken the string value I entered and printed it 10 times. And that's not what I want. A number in programming has different qualities than a string. Programming languages don't treat a number like a collection of characters. Instead, a number is an amount, like a lump of clay. It's easy to see what a multiple of a lump of clay would be. But a multiple of a specific arrangement of characters, like building blocks, is just a repetition of that arrangement. To be able to do math with my input, I need to convert the user's entry to a number data type, and then I can do math with the converted number. So if I go back to my program before the multiplication statement, I'll create a new variable, and that'll be value underscore int, and I'm going to set that equal to int parentheses value. The int method converts a string to an integer, which is a number without a decimal portion. Python also supports converting a string to a number that includes a decimal portion using the float method. The statement I entered saves the integer version of the value with the variable name valueInt. And then I need to update my print statement to use the value underscore int variable name. Now, when I save my program and I run it, and I type in 50 as the number, I get the result 500, which is what we get when we multiply 50 times 10. You can do all sorts of manipulation with data, including string concatenation. But it's important to remember that the ways you can change a piece of data are limited by the type of data. Sometimes accomplishing what you want involves first changing the data to the appropriate type. I can do a lot of things with an assembled set of blocks, even just a single row. I can change out certain blocks. I can remove or replace certain blocks. I can break the sequence apart at certain points. I can even pull it all apart into individual blocks. Most programming languages include tools that let us do similar things with strings, and often a lot more. But when would we want to change the content of a string in our programs? Well, imagine writing a program that receives data that a user has typed into a form, for instance. The user enters first and last name, and you want to add that to your database. But what if the user enters a name in all lowercase? Maybe you want to ensure that the first name and last name are capitalized. This is one place where string methods can be really useful. In the start file for this video, I've included a few variables. Notice that the first name isn't capitalized and neither is the last name. So first up, I want to transform those names into names with initial caps. Python includes methods that work on any string. You just reference the string followed by a dot and the method name. To capitalize the first letter of a string, I can use the dot upper method. I'll create a new variable, so first underscore name underscore cap, and the value is going to be a reference to the first underscore name variable, which is all lowercase, followed by a dot and the capitalize method. When I use a method, I always include parentheses at the end. In this case, I don't need to provide any argument in the parentheses, but arguments are useful for some other methods. And then I'll create a similar statement for the last name value. So last name cap equals last name dot capitalize. Then I'll add statements to print both of those values. So print first name cap and print last name cap. And I'll save that, and then I'll execute my code. And in the terminal, I see the first and last names printed, but with initial caps. So Malala now starts with a capital M, and Yousufzai starts with a capital Y. It's also pretty common to need to search for specific characters in a string. For instance, you may simply want to search for a certain word or phrase within a string. Python has several string methods that let you look for text. The find and index methods give you a reference to the first occurrence of text you specify, while the rfind and rindex methods provide the last occurrence. My note variable contains the label award and a colon and space before the name of the award. Assuming I don't know the value of the note variable before I work on it, it can be useful to check if that text is part of the value. I'll create a new variable, award location, and for the value, I can use note.find and then in parens the string award colon space. And then another statement where I'll print that variable, award location. And then I'll save that and I'll execute it. And I see in my terminal that the value that's logged is 0. The find method returns the location of the start of the text I searched for within the string. And it indicates the location by numbering the characters starting with 0. So a value of 0 indicates that the text I was looking for occurs at the start of the string. Now that I know this text is part of the string, I want to get the text that comes after it, the actual description of the award. Getting part of a string value is known as slicing. In Python, you don't need a method for this like you would with concatenation. Instead, you use something called slice notation. With slice notation, I add square brackets after the reference to the string, and I specify the characters I want. I can indicate both the start position and end position separated by a colon. I can also leave out one or the other. Leaving out start means the slice starts at the beginning of the string, and leaving out the end means it goes to the last character. In my note variable, the award label is present, so I know it occupies positions 0 through 6. So I want to slice the remainder starting at position 7. So I'll create one more variable, award text, and then for the value, I'll reference note, I'll add my square brackets, and I want 7 as my start position, and then a colon. And I want to go to the end of the string so I don't enter an end value. And then I want to add a statement to print that. Now I save and run in the terminal, and there's just the award name, Nobel Peace Prize. String methods provide your code lots of flexibility to deal with strings that may need some tweaking or massaging before you can put them to their intended use. You can also chain methods one after the other to do more complex transformations. When I do this in my code, I often end up feeling like I've solved a really intricate puzzle. It's super satisfying when I see that result that I was working toward. Sometimes working with patterns requires more complicated searching in order to do the manipulation you need. Say I want to find every instance in this pattern where a yellow brick is followed by one or more red bricks, and replace that whole sequence with a single blue brick. I don't want to replace just the yellow bricks, and replacing each yellow followed by one red might still leave some red bricks that I want to replace. So my process has to be really detailed and meticulous. Strings sometimes need complex searches and manipulations too. Many programming languages, including Python, allow you to do this by supporting regular expressions. A regular expression lets you create a description of a pattern that you want to match. You can then check a string against the regular expression, and if it matches, you can use one or more methods to work with the results. A regular expression is also known as a regex or regex, and can be made up of letters, numbers, and special characters. But within a regular expression, each character has a specific meaning, and you can put them together to describe exactly what you need. For instance, you can indicate specific text you're looking for by enclosing it in slashes. Backslashes mark many patterns in a regular expression. For instance, \d indicates a digit, \w indicates a word character like a letter, and dot indicates any character. You use the plus sign to indicate one or more occurrences of the preceding pattern. Asterisk indicates 0 or more, and question mark indicates 0 or 1. Let's explore how this works. The file for this video starts with an import statement for the RE module, which contains methods for creating and working with regular expressions. Then it contains 3 variables: a US 5-digit zip code, a US 9-digit zip code, and a North American phone number. I want to write a regular expression that will identify whether a variable contains 5 digits in a row, which is the minimum for a US zip code. I'll start by creating a variable, 5-digit expression, and then for the value, I start with the letter R. This indicates that the string that follows may include backslashes that the compiler should ignore. After that, I include my expression in quotes. And I simply want to look for 5 digits, so that's \d followed by curly braces 5, which denotes 5 occurrences of the preceding expression, the digit. Now that I have a regular expression, I want my program to compare it to my strings. So I'll use a print command. And in the parens, I'll call the re.search method. And that takes 2 arguments in parens, the regular expression and the string to compare against it. So 5-digit expression as the expression, and then 5-digit zip as the value to search against. Then what I want to do is copy that whole statement and paste it in a couple more times, and then just tweak the ones that I've pasted in to search against the other 2 variables I've created. So instead of 5-digit zip for the second one, I'm going to search against 9-digit zip, my second variable, and then for the third one, I'm going to replace that string reference with phone_number. And now I have a print statement that's using a regular expression search method to search against each of those strings using the regular expression I created. Then I'm going to save that and run it. And in the terminal, I get 3 results. The first 2 are match objects. These are returned when the string matches the expression. And this makes sense because both the first and second string contain 5 digits in a row. The third value printed at the terminal is none, meaning that the third string didn't match the regular expression. And I expect that because a phone number doesn't include 5 digits in a row. Creating a regular expression can be a complex task. For instance, this is one stab at an expression that matches all possible email addresses. It has to take a lot of factors into account. Fortunately, regular expressions are already written for many common patterns, so you don't need to create something as complicated as this right off the bat. Being able to recognize a regular expression when you see one is an important first step. Using Python documentation and basic building blocks, you can break down existing regular expressions to understand what each component means. Then when you're ready, you can start building your own. You've learned the basics of working with and manipulating strings. Now try your hand at putting them to use. The start file for this video includes a statement that prompts the user for a distance in miles and saves the result with the variable name miles. It also contains a comment that describes the formula for converting miles to kilometers. Your task is to take the value entered by the user, convert it to a value in kilometers, and then print the result to the terminal with a text description using string concatenation. Remember that you can convert a string to a number containing decimal places using Python's float method. This challenge should take you about 15 to 20 minutes. Join me in the next video and I'll walk you through how I approached it. Have fun! I hope you had fun with that challenge. I enjoy programming puzzles that involve working with strings, but there are a number of moving parts here, so if you felt overwhelmed, don't worry. As you get more familiar with string manipulation and methods, you'll become more comfortable with doing this kind of coding. For now, let me show you how I solved this. I have some code to start with, and if I run that in the terminal, I get a prompt to enter a number, and that's it. There's nothing more in my code right now. I also have a comment containing a formula for converting a value in miles to kilometers. Remember that the value a user types in response to a prompt is treated by Python as string data. I want to do a calculation with the number that the user enters, but I can't do that with a string. So my next step has to be to convert that string to a number. Python has a couple different number data types. Integers don't include decimals, while floats do. Since I'm doing a calculation here, I'll want to allow for decimals. So I'll create a new variable called milesFloat, and I'll use the float method to convert the miles string to a float, a number with decimals. Now that I have a value in miles, I can use my formula to do some math on it and convert it to kilometers. I'll create a new variable called kilometers, and then I just need to multiply miles_float, which is what the user typed in, converted to a numerical data type, by this value that I have up here for conversion, 1.6 and some change. So I'm just going to copy and paste that in. And then I'm going to print a label for my data. So I'm going to print that value in kilometers is, and then finally, I want to print the number that I calculated to the terminal. So print kilometers. I'll save those changes. I will execute my code. At that prompt, I'll type 50. And the response I get is my label, that value in kilometers is, followed by the result, which is 80 and some change. And that makes sense. 1.6 times 50 is about 80. Now, what would happen if you tried to do a calculation on what the user entered, which is a string? So maybe you converted in your code to a float, but then forgot and still used the original miles variable rather than milesFloat in your calculation. Let's try that out just to see. I'll change my equation to reference miles rather than milesFloat. Then I'll save and I'll run that. And at the terminal, I'll type in 50. And I get an error, and in particular a type error. And that's because I'm trying to multiply a string and a value. A type error is a good indication that you need to convert one of your pieces of data to match the other. I hope you enjoyed this challenge. If you got it to work all on your own, congratulations. And if not, that's okay. In fact, part of programming is testing your limits, identifying what you need to brush up on, and then practicing some more. Keep at it, and over time, you'll get more comfortable with string manipulation. When I get out my tool bag to work on a project, I have some decisions to make about which tools I pick and how I use them. There are some uses of tools that are generally just a bad idea, and it's widely agreed we don't want to do, like using pliers to try to unscrew a nut, which can damage the head to the point that it can no longer be removed. If I'm working for someone else, they may dictate which tools to use for which tasks. For instance, my boss might require that I use a nail gun rather than a hammer so I can work more quickly. And sometimes the choice is totally up to me. I could use a straight driver with a socket head to unscrew a hex nut, or I could use a ratchet, and I'd get the same result with about the same amount of effort either way. I can decide which feels more comfortable, which is easier, or which I just like more. In any programming language, as you learn more about the available syntax and structures, you'll discover multiple ways to accomplish the same task, and you'll have to choose among them and decide the best way to build the program you're trying to create. And just like with tools, there are some constructions to avoid, some that are accepted standards, and some that are totally up to your preference. Whether you're starting out or you're an experienced programmer, it can be helpful to consider the choices that other developers make when writing your own code. This is such a common need that developers create and share documentation of their approaches to code. These documents are known as style guides. Online style guides are available for all major programming languages, and often you'll find many style guides available for a given language, with some commonalities and some differences among them. In most languages, though, a small number of style guides are considered industry standards. Consulting these can help you understand some of the most common approaches and often the thinking behind them. For Python developers, the most commonly used style guide is called PEP 8, which is short for Python Enhancement Proposal number 8. As I write Python code, I can consult this style guide if I have a choice to make in my coding approach. PEP 8 even covers some of the very basics of coding. For instance, Python relies on indentation to indicate the content of structures like conditionals and functions. But does it matter how many spaces I use? 2, 3, 4, more? In the PEP 8 documentation, indentation is one of the first things that's covered and unequivocally recommends 4 spaces. We even have a few examples of what properly indented code looks like. How about quotes? Python allows single quotes or double quotes around strings and other objects. Which should I use? Clicking the string quotes heading on pep8.org, this style guide says either is fine. Just pick one and stick to it. This is a situation where you might find that a particular project or workplace expects everyone contributing to the same code to use the same style, so you may very well be asked to use one or the other. But if you're just working on your own projects, you can pick whichever works best for you. Other popular style guides exist for Python, like the Google Python Style Guide, and other languages have respected references of their own. For instance, one of the most commonly used style guides for JavaScript was created for internal use by Airbnb, but is now widely consulted as an industry standard. You don't need to worry about memorizing style guides, but especially when you're not sure about a choice you need to make in your code, or if you see code written by other people that takes a different approach to your own, style guides can be valuable resources in understanding the trade-offs and helping you write code that's as efficient and understandable as possible. I want to take a trip. I want to go to Tokyo to see a Grand Sumo match, and I want to visit Seoul as well while I'm on the trip. I know the range of dates when sumo matches take place, but otherwise, my plans are somewhat flexible. I can start by researching other events that I might want to attend and when they are, things I might want to see, and getting tips from friends who've lived or visited either place on travel and accommodations. I can use all that information to make some decisions on when I want to be in which place, and then I can start actually making reservations and planning the details of my trip. The initial planning step is important because I don't want to end up buying a plane ticket to Seoul, for instance, when there's an event I want to be at in Tokyo. When developers write code, it's common to start with a planning phase known as pseudocoding. But don't worry, pseudocode isn't another coding language that you need to learn. Just the opposite, actually. Writing pseudocode involves simply writing a description of what you're trying to do using plain language. Pseudocoding helps you create a basic outline of the program you're creating. Just the process of writing pseudocode can help you map out exactly what your program will need to do. With pseudocode, you can begin to describe the structure of your program. Pseudocode also frees you from having to decide on a specific syntax to use or even a specific language. Instead, you simply describe what you need to accomplish. For developers who are familiar with multiple programming languages, the process of pseudocoding can sometimes clarify whether one particular language might be a better choice given the structure and scope of what they want to build. When your pseudocode is done, you're left with an outline for your program, which you can then build out using a programming language. With the big picture decisions made, you're ready at that point to get into the details like language and syntax. It can be tempting to skip pseudocoding and dig right into the code. The danger here is that you can get deep into coding before you realize that you haven't accounted for a certain task or behavior, which might require you to start over with a new structure. It's like booking a hotel before you've really thought through how many nights you'll be in that city, or even when you'll arrive. Thinking through and writing down your plans first, through the process of pseudocoding, helps you ensure that when you start coding, you have a sense of where you're going, and you have the main factors accounted for. So be sure to include planning as the first step when you're creating a program. I promise it will help you ensure that you get where you want to go. I'm a programmer, so I keep my favorite recipes organized in an app on my phone. But there's some people who prefer physical copies and rely on paper for keeping the recipes organized. If, say, a friend shares a recipe with me, bringing that data into my app involves an extra step. For instance, I can use a scanner like this one to get a pretty good digital version of what's printed, and then import that into my app. Likewise, if I want to share one of my electronic recipes with a friend who prefers to have things written on paper, I can make a hard copy using the printer. This flow of data in and out of a process is common in many situations, including programming. Simple programs can be a basic set of steps that accomplish a set task every time they run. For instance, you could write a program that waits for a user to type something and then simply prints, "Thank you for your input." But our programs become much more interesting and useful when they can accept different kinds of data and then provide results based on that data. In programming, we talk about this flow of data as input and output, or I/O for short. Input can take many different forms depending on the program. For instance, a program that plays music can take a stream of digitally encoded music coming from an online source as its input. A program created by a data scientist might take a formatted set of data collected in a scientific study as its input. A program can do all sorts of things with data. For instance, if you like a lot of bass in your music, most music programs will let you adjust the specific audio levels to exactly where you want them to be. Or, if you want to figure out when you're getting the most traffic on your website, data analytics software can identify and report the peak times that people visit. When the program has done what you requested, that final result is the output. The output can go all sorts of places. That music program might forward the output stream of music data to be played on speakers. Or the result of your website traffic analysis might be saved to a file to be shared and analyzed further. Not all programming environments support all kinds of input or output. This means if the scope of your project involves input and output, it's important to plan the structure of your code and the languages you want to use before writing a single line of code. By choosing your tools and making a plan, you can build programs that can access information, work with it, and make it available when they're done. Data input and output can take a number of forms. At its most basic, a program can simply prompt a user to enter data and then work with the user's response. In Python, you can collect user info at the command line using the input method, which pauses your program and gives the user the opportunity to type a response. When the user presses enter, the program resumes, and it can then incorporate the user's response into any processing and output. But many tasks require more data than a user can enter by typing. In these situations, your program can access other methods of input, like opening a file from your computer. For instance, to use a word processing program like Microsoft Word or Google Docs, you often start by opening an existing file that you've saved on your computer or in the cloud. When the processing is done, your program can write the results back to the same file or to another file. This preserves the results of the program's work even after the program finishes executing. This is the addvalues.py file, which is in the begin folder for this video. This file contains a simple Python program that reads input from an external file, performs some processing, and then writes output to another file. This program uses a few Python methods that are specific to input and output. The code in the first couple lines uses the open method. This opens files with specific names that are located in the same folder as the program file. I can see the values.txt file in the files list. Opening this file, I can see that it contains a list of numbers. I also notice the file list doesn't contain a valuestotal.txt file. When a file doesn't exist, Python will create it. The program will use the new valuestotal.txt file to store the output of this program. Line 3 and line 10 both use a simple print statement, which is one way of providing output. But simply passing a string to the print method sends that output to the command line. That data is temporary, and when a user exits the terminal, the output is gone. The for loop is doing something different. It's taking one line of the input file at a time, which is one number at a time. Now that number is encoded as a string, so it's converting that to an integer and then adding it to the sum variable. When the program has looped through all of the lines in the values.txt file, the sum variable should contain the total of all the numbers. The for loop also includes a print statement, which is printing the current line with any line-ending characters stripped out. But there's an extra argument here that specifies that the data should be printed to a file and specifies the out file, which is the valuestotal.txt file. So when I'm done, I should see the list of numbers recreated in the output file. After the loop is completed, there's one other print command. This prints the word total and a comma, followed by the value of the sum variable converted to a string. And this print statement is also directed to valuestotal.txt. Finally, we have the close statement, which indicates that the program is finished writing to the valuestotal.txt file. When I run the file, I get an error in the terminal. This is an error you may or may not run into when you're following along, depending how your editor is configured. But if you're also running into this error, we can fix it pretty easily. Let's go to the Settings menu. And I'm on a Mac, so if you're on a PC, this will look a little different. And then in the Search Settings box, I'm going to search for Python and execute. And my editor shows me a few commands for Python that relate to executing code. And this is the one that's going to help me fix my error. Execute in FileDir or file directory. So I check that, and this just tells the editor that when I run a Python file and it mentions another file, in this case values.txt, it should look in the same directory for my other file. So I'll close up my settings, and let me try and run my code again. Now when I run my code, I see the statements processing input and output complete in the terminal almost immediately. The processing my program is doing is pretty minimal, but if it was more involved, statements like this could be useful to let the user know where in the process my program is. Over in the file list, I also notice the newly created valuestotal.txt file. I'm going to open that up, and I see the same list of values as in values.txt, along with the total at the bottom. So the result of my program's processing has been written to a new file and saved. Sending output directly to the user interface or saving to a file both have their uses. What kind of program could you create that interacts directly with a user? Where could writing output to a file really be valuable? As you're putting your programming skills into practice, let your imagination guide you. Try things out and have fun with it. I'm trying to use my drill, but it doesn't work. To figure out what's wrong, and if it's a problem I can fix, I might need to go through some testing. Is the battery all the way in? Yup. Is the battery charged up? Well, I can swap out, grab a battery that I know just came off the charger. Still no love. Oh wait, the switch doesn't move when I push it. I engage the safety lock. If I switch that off, the drill works. After you write a program, it has to be executed in order for you to see the results. But even the best developer writes code from time to time that includes errors or bugs. Just like a broken drill, a computer program with a bug doesn't run as expected, or may not run at all. But not all bugs are the same. The process of identifying and fixing bugs is known as debugging, and it's an important skill for every programmer. There are three main types of bugs in computer programs. A program has a syntax error when it includes code that doesn't match the rules of the language. For instance, if I wrote a conditional in Python without including a after the if statement, my code wouldn't execute because the Python interpreter wouldn't be able to identify the end of that particular statement. It's the same thing if I misspell a word, like if I say PIRNT instead of print. Sometimes your code can comply with all the rules of the language, but still not execute successfully. For instance, suppose you include a call to a function that isn't ever defined. A function call is a valid statement, but when the interpreter tries to run your code, it won't be able to find and execute the function specified in your function call. This type of bug is known as a runtime error because it often isn't obvious until the code is actually run. A third type of error happens when you write code that runs but doesn't produce the results you expect. For instance, a loop that counts in the wrong direction continues infinitely, and as a result, the program never completes execution. This is known as a logic error because while the statements themselves constitute valid code, the result of the statements isn't what you were trying to achieve when you wrote the code. Debugging is just a part of programming. Every programming language has tools available that help programmers identify bugs, and in some cases, suggest how to fix them. But using those tools successfully requires that you take a methodical approach to identifying and then fixing errors. When your code doesn't run as you expect, remember that it may contain more than one bug. However, execution will generally fail at just one point. You can work with the feedback provided by your tools to fix the indicated bug, but afterwards it's important to retest and follow up on any other error messages or other issues that crop up after that first bug is fixed. You'll need to repeat this cycle until your program finally executes successfully and works as you intend. Rather than seeing debugging as a chore, I try to look at it as an interesting puzzle to solve. I encourage you to approach debugging as an opportunity to learn more about programming in general and about the specific language you're working in. When you write code in most programming languages, you're generally just writing text. In theory, you could write your code in a basic text editor, save your code, and then use the appropriate interpreter to execute it. However, there's a wide selection of dedicated code editors, which are also known as Integrated Development Environments, or IDEs. IDEs are built specifically for writing code in different languages. What makes an IDE special is that when it's properly configured for the language you're coding in, it can not only catch bugs, but it can help you avoid creating some of them in the first place. I'm using Visual Studio Code as my IDE, and I've installed an extension for Python syntax support. This means that whenever I open or type code in a Python file, the editor does a few things. First, it parses the syntax of the code and highlights different types of code in different colors. This feature is known as syntax highlighting, and it makes it easier to read through code and recognize what each part of each statement is doing. For instance, here the variable name value is in white, and the method names range and print are in yellow. Syntax highlighting really shines in complex code. Instead of needing to read through a wall of text that's all the same color, the different colors help you visualize the functions of different pieces of code and understand it more quickly. An IDE can also offer to finish code for you while you're typing, saving you some keystrokes, and also helping you avoid spelling mistakes. This feature is known as auto-completion. I want to add another print statement at the end of my program here. So on line 3, I'm going to type P. And I see a list of possibilities that all start with the letter P. There's a lot of them. So I'll continue on and type R. And now the list is narrowed to just 5 options that start with the letters PR. And the first is the print method that I want to use. Now I could switch to my mouse and click the item from the list. But sticking with the keyboard, I can also just press Tab to select the current item in the list and move on. Then when I type my opening paren, the IDE automatically adds a closing paren for me. And it also displays a short synopsis of how the syntax works for the Python print method, in case I need to check which order the arguments go in, for instance. Once I start typing in the parens, the pop-up goes away. I'm going to say all done. Syntax highlighting and code completion are useful tools, but IDEs can do even more for developers. In many languages, an IDE can check code for bugs before you even execute it. This process is known as linting. For instance, what if I type my variable reference on line 2 incorrectly using val instead of value? Let me make that change. And then when I save that code, a squiggly line is displayed under the text val. When I move my mouse pointer over that part of the code, a pop-up explains that the variable val is undefined. My program is relatively small, just 3 lines, so it's pretty straightforward for me to scan the code and recognize that I probably meant to reference the value variable on line 1. But in a larger, more complex program with a lot more lines of code, it can take more work to trace down the source of that error and figure out how to fix the error. Here, I can edit val back to value, and then when I save my changes, that squiggle goes away and my code passes the IDE's linting process. Different IDEs are optimized for different programming languages. When you're learning a new programming language, it can be useful to research which IDEs are commonly used by developers in that language. Picking the right IDE for a language ensures that you have the best tools to write code accurately and efficiently. When you run code that includes bugs, most interpreters provide some information about the error they encountered and where it was located. Occasionally, these messages are straightforward and make it easy to find and fix errors. But more often, these messages only provide a starting point for further research. Error messages can describe a general type of issue rather than explain specifically what the issue might be in your code. And although interpreters often indicate where the issue cropped up while interpreting the code, the actual error may be in a different place in your code, but only became a problem at the indicated point. So it's important to take error messages as clues, but not solutions. The compare.py file contains a variable definition, followed by a conditional statement that prints a string. Immediately when I open it, I see a squiggle under the number 60. When I move my mouse over that code, the linter tells me invalid syntax, but that's all. So I'm going to run the file and see what the interpreter reports at the terminal. At the end of the output, I get that same message, syntax error, invalid syntax. But above that, I see one of my lines of code with a caret symbol on the line below it. It's common for interpreters to use this 2-line layout to describe errors, with the caret pointing to the character in the code where the interpreter ran into the problem. With my attention directed to the end of the line, it's a little easier to recognize what's missing, the colon. So I'll add that, and I'll save. The squiggle disappears under the value 60, so I've fixed my error. But now, a red squiggle shows up in the next line. This is one of those cases where fixing one error reveals another one. And when I move my mouse pointer over the new squiggle, I again get that report, invalid syntax, but that's all. So once again, I'm going to run the code in the terminal. And first I'm going to click down here and I'm going to clear that terminal out. On a Mac, that's Command K. Then I'm going to run my code again. And again, I get the line of code reproduced with a caret pointing to the letter A in the middle of the line. This can be an easy error to overlook, but in general, when an interpreter has a problem in the middle of a string value, it's a sign that the interpreter is trying to interpret the string itself as code rather than treating it as a single piece of data. And once I recognize that, I realize I forgot to include the quotes around the string. So I'll add those in. and I'll save. And now that's fixed. That squiggle is gone under the letter A. But my IDE flags another issue back up on line 3. And this time, if I move the mouse pointer over it, that pop-up does a pretty good job describing the issue, undefined variable. And if I look at my code, here I'm using temp as the variable name, but above I defined the variable using the name temperature. Now to keep my process consistent, I'm going to go ahead and clear my terminal and run the code one more time. And in this case, the terminal reports the same thing, just using slightly different language. So on line 3, I'll change temp to temperature, and I'll save that, and no more errors are flagged. So now I'll run one more time, and bring a jacket is printed to the terminal, which is exactly what I expect. As you build experience reading error messages and fixing bugs, it should get easier to understand what specific messages might mean. And once you understand their meaning, it's easier to keep debugging until every error is fixed. Sometimes error messages are very descriptive, and sometimes they're more vague. But it's also possible to have an error without an error message. In the count.py file, I don't have any squiggles indicating errors in the code. The idea here is that my loop will count down from 10 and print each number to the terminal until it hits 0. So I'm going to run that at the terminal. And I get the message saying which file was executed, but that's it. No other output. Here, the code is being correctly interpreted, but the results aren't what I expect. In this situation, the debugging is all on me. I need to think through my code from the computer's point of view and identify where the code is different from the instructions I meant to give. I'm starting with an I value of 10, and then I'm looping for as long as I is less than 0. Now the starting value of 10 is not less than 0, and that means the statements in the loop are never executed. That leads to exactly the output I saw. What I want instead is for the loop to run as long as I is greater than 0, which is the other angle bracket symbol. And I mix these up all the time. I'll fix that, and I'll save that. I'm going to clear my terminal. And now when I run it, I can see 8 at the top. I'll scroll up a little bit. So I got my count starting at 9 and going all the way down to 0. Success! As you get more practice coding, you'll probably start to recognize specific types of errors that you tend to make. I can't tell you how many times I've used greater than when I meant less than, and vice versa. So I know to be on the lookout for that. Sometimes putting the clues together to track down a bug can take a lot of work, and it can even be frustrating, especially when you have a deadline. When you're working on a bug and not getting anywhere, try walking away from your computer for a few minutes and letting your mind wander. It might seem counterintuitive, but sometimes stepping away and coming back to the problem with fresh eyes can be just what you need to identify the problem and get your program working. I have an important meeting in the morning, so I need to set my alarm clock. Before I go to sleep, I want to make sure the alarm clock is going to wake me up. So I'll temporarily change the alarm to right now. Now I heard a click, but nothing else happens. and that is not going to wake me up. So I check a few things. Well, the alarm is turned on, the hands are lined up. Oh, there's no battery. So let me rectify that. And now the alarm works. So now I know my alarm clock will do what I need, and I can set the alarm and go to sleep. When I've written a program that performs as I expect, and my interpreter doesn't report any bugs, it can still be helpful to do a little more testing. Especially for more complex code, it can take multiple tests planned out in a thoughtful way to ensure that I'm actually testing all of the possible use cases and every line of my code in all of the possible combinations. To do this kind of testing, programmers create test cases, which are commands or scripts that use the program in a way designed to test a specific scenario. In the forecast.py file, I have a function that takes a temperature in Celsius as an argument, and then uses a set of if and elif statements to decide what advice to print. To fully test this program, I want to execute it with a statement that evaluates to true for the if clause, and another statement that's true for the first elif, and a third that's true for the second elif. That way, I can verify that values in those 3 different ranges each produce the results I expect. When you're working on a larger program, it's common to use an entirely separate application for testing your program. But we can create basic test cases within our Python file just by calling this function with specific values. So I'll write some statements to call checkTemp, first with a value of 10, and I'll call it again with a value of 30, and finally, call it one more time with a value of 37. These values land within the ranges of each of the 3 conditions. When I run my code, I expect each of the print statements to be printed in order. So I'll save, and then I'll run. And the results are not what I expect. My first test case results in the 3rd print statement being printed. But obviously, I don't want to leave the jacket at home for a temperature below 15. But reviewing the first condition, I notice I coded it wrong. It's supposed to be for cooler conditions, but it's checking whether the value is above 15. So I'll change that sign. It needs to be a less than. And then I'll save it. I'll clear my console. And I'll run again. And now I see wear a jacket printed first, followed by pack a jacket. But the 3rd statement, leave the jacket at home, is never printed. I need to examine that condition again. And when I do, I notice I once again got the sign backward. I'm checking for a temperature below 35, but I really mean to check for above 35. So I'll swap that sign. Instead of less than, I want greater than. Then I'm going to save that. I'm going to clear the console, and I'm going to run my code again. And now I get all 3 statements printed in order, which is what I expect. Test cases can be challenging to write, and personally, when I have an exciting new feature that I want to create, building test cases can feel like a much less interesting task. But test cases are a really useful tool to ensure consistent results from your app and the best possible user experience. Ready for another challenge? Now that you're familiar with the basics of debugging, try your hand at finding and fixing basic errors in some Python code. The start file for this video is supposed to recommend a houseplant based on the level of care the user can give, low, medium, or high. But when I run it, I can see that it's not working. Here's a hint. This code contains a syntax error, a runtime error, and a logic error. Remember, you can use both your IDE and the terminal output to identify where the interpreter encounters each error. We talked about how debugging can be challenging, so if you get stuck, consider trying a trick that many developers are fond of. Explain your code to a rubber duck. When I type one of three keywords, the program should recommend a houseplant, but it's not returning anything. Maybe I need to look at those if and elif statements and look for possible errors there. It's super common to find that explaining the problem to a colleague, a friend, or even an inanimate object like a rubber duck can help you think about it in a different way and perhaps help you notice something to try or check. This challenge should take you about 10 to 15 minutes. Join me in the next video and I'll walk you through how I approached it. Have fun! Hope you had fun with that challenge. You might have had questions while doing it, or you might have had a moment when you weren't sure about what to do next. If so, that's totally normal. Understanding and working with programming concepts takes practice. In fact, even experienced developers run into errors they can't easily fix. Trying your hand at this challenge is a first step in building those muscles. When I open the file, I notice right off the bat that I have a red squiggle on line 2. And moving the pointer over that, the linter tells me I have invalid syntax. But if I run it, the terminal includes a caret that points out the location in the line where it found the problem, which is the equal sign. And that's enough to remind me that I need a double equal sign for comparison. So I'm going to add in another equal sign here. I'm going to save that. And now my syntax error is gone. That red squiggle is no more. But now I have a red squiggle on line 9. And when I hover over that, the linter error is undefined variable. Now if I look up at the start of my code, the name of the function I'm calling is plant recommendation, not plant rec. So I can fix that, even using autocompletion. So that's my runtime error fixed. I save, and the IDE doesn't flag anything else. So I'll run my code in the terminal. I have 3 test cases in my file, but only 2 values are printed to the terminal, allo and pothos. The third case, with the value high, should trigger the second elif statement. So I'll look at that statement more carefully. And I notice that I repeated medium as the value for checking rather than high. This is a logic error. So in that second elif statement, I'll replace medium with high, and I'll save my code. I'll clear my terminal, and I'll run one more time. And now I see all 3 possible results printed in the order I expect. You may have found all the bugs right away, or you may have taken a while or not found them all. That's okay. Debugging takes work, and bugs aren't always obvious. Fortunately, debugging is a skill that you get better at the more you do it, and there's never any shortage of bugs when it comes to programming. Approach debugging with curiosity and a sense of adventure, and you'll continue to level up on your programming skills.